is when it was interrupted, I remembered the word. It is bioinformatics. This science is called bioinformatics. Mm. It is still developing informatics. So it is still like in the period of growth. It has not achieved its final results. Well, if you are yourself a specialist in bioinformatics, you can just say that it is so. But if you have perhaps some friends working in these fields, so you can understand it. I spoke with one of the students and he said, well, for me, sometimes I lose hope that we will eventually find the sort of decipher the DNA. So it seems that it consists of it is like information is written in some unknown language, like Egyptian language, and we don't know how to understand these letters. Okay, well, of course, we know many things, but not all is clear. We don't have a complete picture. Well, this can be compared with, say, Copernicus. He, of course, saw something. He made just a great discovery or just a bold hypothesis. He put sort of like launched Earth in motion. So the same was with the genetics. This idea that DNA contains some information, some genetic code, and this is, of course, a very fruitful idea. But we're still waiting for complete picture. Okay, when complete picture will be achieved, then we'll have a new paradigm in biology, but we still don't have it. um, Also, we don't understand something in physics also. For example, we could understand the mechanism of just superconductivity, normal superconductivity, but now we have high temperature superconductivity, and the mechanism of high temperature superconductivity we cannot understand. So in also in condensed state physics, there is also not all clear. So we are also still waiting for some new insights. Well, I think it's everywhere, even in uh, well, the big breakthrough was the so-called expanding universe or Big Bang cosmology, which was not complete when Thomas Kuhn wrote his famous book. For example, even well, why? Because only in 1965 was uh, found the so-called black, the so-called background radiation, back background radiation of 3 kelvins um, radiation, background radiation. You know this radiation, which is 3 kelvins, corresponds to it is radio waves, which corresponds to 3 kelvins. Okay, background radiation. Angel Sierra, you know it, yes?
Yes, yes, background.
So, but it was found just accidentally. Penzias and Wilson, they received later the Nobel Prize for that. Penzias, I think like this, Penzias and Wilson. They received Nobel Prize for that discovery, but they did it not on purpose, but accidentally. They found some like radiation in well, corresponding to waves which are in radio what's like radio waves. 3 kelvins correspond to radio waves. You know, if you take this like course, well, if you take temperature, you know that there's a formula which connects temperature with frequency. So if we take this formula, we can see that, well, it is only valid for the so-called black body radiation, which is in like in equilibrium with the body from which radiation is emitted. So the hypothesis is that when our universe just started to exist, it was very hot. So the radiation which it emitted was in thermal equilibrium with the universe itself. But as it expanded, it became colder because adiabatic expansion creates like decrease in temperature. So according to this concept, our universe is cooling down. So it starts to being cold. And now its temperature is about 3 Kelvin. And the wavelength of the radiation, which is in equilibrium with this temperature, is radio waves, okay? So these radio waves were experimentally detected. And that is why the this is how this Big Bang cosmology, or the cosmology of the expanding universe, was finally sort of proved. Also, even in the 60s, you could read in some uh, textbooks that they didn't understand, the physicists at that time, why in more distant galaxies there is higher percentage of hydrogen than in those galaxies which are closer to us. But now we can understand it, because the galaxies which are far away from us, we see them still young. When If we take into consideration the time that light has to pass to us, okay? So when we observe them still young. Now they are much older, you see? So when we observe this matter on these young galaxies, the matter on its first stages, of course, the percentage of hydrogen, which is the so-called uh, fuel of the stars, okay, hydrogen, is higher than with the old galaxies, the galaxies which already exist for several billion years. So in these galaxies, helium is much higher concentrations than in young galaxies. So at that time, in the 60s, it was still not clear why it is so. Now, when the Big Bang cosmology becomes also a scientific paradigm and a standard model, as it is called, uh, yes, cosmic microwave background radiation, yes, of course, cosmic, okay. So now it is just essentials. And we can say that the mature paradigm came when Steven Weinberg or Hawking, well, I prefer the book by Steven Weinberg. It is popular one. It's called First 3 Minutes. Steven Weinberg. First 3 minutes. Um, Here you can see the just standard model explained. First 3 minutes. This is a theory of a so-called expanding and hot universe, or Big Bang cosmology. But at the times of Thomas Kuhn, when Thomas Kuhn wrote his book, The Structure of Scientific Revolutions, this was only in process. We couldn't just say that Big Bang cosmology was accepted by everybody. There was also a concept of stationary universe and uh, well, other like concepts which not all physicists accepted it. Now it is more this the enemies of this Big Bang cosmology die out, have died out. So I think the younger generation, for example, your generation, is I would say, educated on this Big Bang cosmology. Well, so we've touched several, how to say, fields of physics and biology also. And we see that somewhere we have interesting breakthroughs. Somewhere we are still waiting for confirmation. Well, for example, quark model of atoms is now a standard one, but we are still waiting with the Higgs boson. We are also received some new confirmation of this quark model. Yes, so we are unfortunately, again, I was, uh, mm, how to say, uh, mm, banished from Zoom, not on my own fault. So now, what are we expecting? And we are expecting some new discoveries, which will maybe breakthroughs giving us some new paradigms, and that is why the theory of Kuhn is interesting for us because it gives us this. Now, and another thing, yes, well, another thing which is also waiting its explanation is, for example, the universal constants or their combination, which is still regarded as contingent. For example, uh, yes, for example, this is a fine, the constant of um, fine structure constant, which is structure constant, which is 1 divided by 137, well, approximately. So we cannot understand why it is dimensionless, okay? So we cannot understand why this figure and not the other. Well, there was in 19th in 1973, already after the book of Thomas Kuhn was written, anthropic principle. What is that? Um, Anthropic principle or fine tuning, um, or fine tuning. What is that? This is also an attempt to explain, say, the fine structure constant. It was argued that organic molecules can form only under the condition that the fine structure constant is what it is now, not more, not less. So this is called fine tuning. So the fine structure constant is tuned to creation of certain important um, like carbon chains which are important for eventually for life. So life is possible only when fine structure constant is what it is, and in other cases, life, organic life as we understand it, would not be developed. Uh, uh, so now we have, now we think, so what it is, maybe it's tuned. So the anthropic principle asserts that then, well, that somehow universe is welcoming man. So universe is a certain system which somehow is tuned or prepared for man's habitation. Well, it seemed quite an interesting turn because it was also like a change of our mentality, because we were not accustomed to think in Aristotelian final causes. You remember that Francis Bacon already despised these causes and called them barren virgins. So they are fruitless in science. These ideas of, um, say, ideas of purpose. But now, with the anthropic principle, the idea of purpose somehow reappears in science. So it can also be regarded as a kind of a breakthrough. But for Thomas Kuhn, it was not relevant because Thomas Kuhn wrote his book, as I explained to you, in 1962. So he didn't touch this question of anthropic principle. So we have plenty of work to do now. I mean, the philosophers of science. We have to um, continue this philosophy of expanding universe. We have to continue with this anthropic principle, with this fine tuning, because it is all these problems are philosophically laden. You understand? So they are philosophically significant, and they demand our reevaluation of the concept of purpose, or this called final causes of Aristotle. So whether they are to be reintroduced, whether we have to rehabilitate them, you understand. This is rehabilitation is very well known for Russians, because many people who were victims of Stalin's purges were under Khrushchev rehabilitated, okay? So the accusations were annulled, okay? And they were restored to normal life. You understand? So now this accusation sort of hangs on these final causes of Aristotle. We still regard these final causes as noxious for, say, strict science. Maybe anthropic principle is a first attempt to reevaluate all this situation and somehow reintroduce these final causes in science. Okay. Well, this is well. Of course, we have a lot of other problems which we'll discuss later. I mean, ethical problems, ecological problems, which also somehow deserve attention and also wait for some breakthroughs in their solving. So we now, what else can we sort of have from this idea of Thomas Kuhn? I mentioned you this idea of incommensurability um, of paradigms. So we cannot find a common measure for, say, classical mechanics and quantum mechanics. Why? because classical mechanics insists on, say, continuous change of momentum and time, for example, uh, and it asserts that we can measure infinitely, well, in principle, infinitely precise the momentum and coordinate of a certain moving body um, in any moment of time. But according to quantum mechanics, there's a so-called uncertainty relation, which sort of denies or um, like forbids us to speak about coordinate and momentum at the same time. So we lose the idea of trajectory, which is very important for Newtonian mechanics, this idea of trajectory. Now we cannot speak in quantum mechanics, we cannot speak about trajectories. Well, also, this incommensurability consists in wave-particle dualism. So, in classical mechanics, we regarded the object either as wave or as particle. Now we see that electrons display wave, uh, mm, how to say, properties of a wave, and waves like photons display their properties of particles. So this is inconceivable in a classical paradigm. The third one is the so-called quantum tunneling or tunneling. Okay, quantum tunneling. Well, it was first proposed in uh, 1928 by Russian physicist Georgy Gamov. Gamov. Uh, this tunneling was this coming of alpha particle through potential barrier, which is unsurmountable in classical mechanics. So quantum tunneling explains the alpha decay, radiation decay. So this was the work done already in 1928. But if we take tunneling, we can see that tunneling is forbidden in classical mechanics. So these potential barriers are unsurmountable in classical mechanics. So according to classical standards, this is like um, uh, the law of so-called law of conservation of energy forbids such processes, but they become uh, sort of, they can occur when we take this uncertainty relation only formulated in different form, that certain uh, that energy and time cannot be sort of measured in the same time. Okay, so there's some uh, uncertainty in it's just written as delta E uh, multiplied now delta t is more or less equal to uh, h, which is the constant, the Planck's constant. Well, this is the formulation. So energy cannot be measured strictly. So if we take very, very short periods of time, then there is a certain uncertainty of energy and that makes it possible for a particle to come through the potential barrier. Okay, so this is the things that make quantum mechanics very different, not only in details but in the main concepts. So that's why Thomas Kuhn insists on incommensurability of paradigms. So what is waiting for us in future perhaps is a new paradigm which will be incommensurable with what we are now accustomed to. So we have to prepare for a new thinking, okay? So we should be bold enough just to take these new ways of thinking, never be sort of um, proud of our achievements, and never be satisfied with what we have, but always think for future and be like oriented in future in or directed in future, centered on future, and be prepared for new ways of thinking, new ideas. This is what we are sort of waiting for, according to Thomas Kuhn. Yes, this is idea. Now, a few words also, just to finish it, about scientific community. Also interesting idea that uh, Thomas Kuhn introduced. What is scientific community? Mm, community. And what is consensus? Community and consensus. Um, well, that is conservative, uh, because before we achieve a new paradigm, before the new paradigm is formulated, scientific community holds the previous paradigm, and it acts as a conservative force. So scientists in general are not glad when they see some new ideas, because they are accustomed to accepted ideas. They are already taught in the universities. So the contents of these, say, textbooks becomes a conservative force, and it somehow, uh, like I would say, uh, um, uh, magnetizes or hypnotizes the young students, and they just couldn't afford to think in different way. They are accustomed to certain ways of thought, and they get used to them, and that is why the scientific progress is somehow stopped. So we can remember in this respect the so-called idols of Francis Bacon, which hamper the progress. Because you remember with these idols of the cave, idols of the tribe, so now we have idols of scientific community. So scientific community acts as a reactionary force. But we cannot do anything with that, because without scientific community, there will be no science. So scientific community is positive. It contains what we already have, codifies already existing knowledge, transmits it to younger generations. Okay, but well, it also unfortunately hampers or say um, does not allow new ideas mm, to appear, because it is conservative. Well, like our organism, it is conservative. It doesn't allow foreign particles to move in it. So it and somehow sometimes it is very beneficial for us, but somehow it can be noxious for us. So this conservatism of scientific community and its will to receive consensus, sometimes it's beneficial, but sometimes it prohibits the new discoveries somehow, uh, just gives an obstacle to new discoveries. Yes, very easily. Scientific community holds and maintains the existing paradigm. Like in the Middle Ages, all the professors were teaching the same things about Aristotle, and all students were taught about these four elements of Aristotle: earth, water, air, and fire. And they received diplomas, became specialists, say doctors or lawyers or theologians or philosophers, just with their mind formed by Aristotelian concepts. And it was very difficult for them to accept, say, Copernicus, Galileo, Descartes. So they were newcomers. They were regarded with suspicion. And even Galileo affair can be regarded in this through these lenses. Okay, so the existing paradigm in theology, in philosophy, in science was very adverse against Galileo, who was regarded as a revolutionary. Okay, and revolutionaries, they can be easily arrested as potential danger for existing society. Okay, existing social order. So that's why there was this. This can explain the conflict between Galileo and the Catholic Church. The Catholic Church was happy with the existing paradigm. It adapted itself to it. And with Galileo, it couldn't find how, say, for example, infinite universe was very foreign to man. Man felt like an orphan in this infinite Newtonian universe. So he was quite happy with this closed Aristotelian world. Everything was understood, explained, easy, familiar. And now all it was like torn to pieces. So change of paradigms is painful. So people don't want pain. They prefer to be, well, live in cozy world, and they don't want to leave the comfort zone, as now people say, to leave the comfort zone. Yes, um, comfort zone. Well, maybe for Indonesia, it's not so important. Yes, uh, Rilon, you don't live in comfort zone in Indonesia because Indonesia is a place of risky life. Yes, not United States in any way. Okay,
Yeah.
Africa also, but India perhaps also. But Europeans and Americans are like comfort. They like expensive cars. They like air conditioning. They like tasty food, or just spare time, to have a lot of spare time. Okay, so to enjoy life. And scientists also are men, so they when they spend a lot of time and energy to master a certain paradigm, they are happy with their teaching positions, with their diplomas, with their ratings, or understand. Yes, and they don't want to just. And what is the new paradigm? It just tells you what you are accustomed to, what you teach to other students, what you were yourself taught is useless, is outdated, is old fashioned. You need to adapt to new discoveries, to new mentality. That can create tensions. Okay, so that's why that explains a lot. So, and well, I think that Kunst theory is especially important for young scientists who are making their first steps in science. You remember that many discoveries were done by young people. Einstein was 26 when he developed his special theory of relativity. Heisenberg was 27 when he produced his uncertainty relation. Niels Bohr was also young when he worked in Cambridge with Rutherford. Rutherford was old and he couldn't understand the young Gamov with his quantum tunneling. Okay, tunneling. So old people are more conservative. I think that young people should appreciate this, um, uh, say, Kuhn's theory of scientific revolutions, because it gives a place to new ideas and to younger generations. Okay. Also, now we have people from, well, we are accustomed, say, to English schools like Cambridge, Oxford, or American universities like Caltech, Massachusetts, Harvard, and say new universities which are created now in Egypt, in Indonesia, in India. They don't have such high rate, as established universities. But this also can be changed, because the development of science, if the next revolution will take place, say, in India or in China or Indonesia, then everything will be changed, and we will have to adapt history of science to new facts. Okay, so maybe you will be the new actors of this play, you see, and of this history. And the future historian will write another history of science that we have now. Okay, so we can't even imagine perhaps what the future history of science will be. So when I'm speaking, I always just am a little bit uncertain in what I'm saying. Okay, that's why I say so much. For so many times I repeat sort of. You perhaps knew this my idea, sort of, because I'm not sure. I'm not just convinced that I'm speaking the whole truth. You understand? I'm only provoking your own way of thinking. So thank you for listening to me. Thank Anshita and all the others. And I hope it was productive for you, notwithstanding difficulties with internet. So I wish
Thank you
you,
for today.
yes, I wish you happy weekend, and hope to meet you next Saturday.